Hello, this is Ryan back with another wacky physics video, and today we're going to be doing this problem right here, which starts us off with drawing a position versus time, velocity versus time, and acceleration versus time plot charts, all vertically stacked, and using the above curve to fill them out, which is actually below. And we have to explain how we calculated the points and then give a plausible story for what is happening in relation to this velocity versus time chart. So we have the story of Georgie here. He's going into an indoor skydiving place, and if you don't know what that is, it's basically where they put you in a tube with a fan at the bottom that's blowing upwards. And the theory is that the speed of the fan is supposed to, the speed at which the fan turns is supposed to keep you up long enough for you to just, or strong enough for you to just float there like you're skydiving. But in poor Georgie's case, he's a bit too heavy, and the fans aren't spinning fast enough for them to keep him up in place. So at first he starts at a position of y equals 2 meters below the starting, like the top of this thing, and he just starts falling. But luckily they gave him a parachute to pull in case such a thing were to happen, and he pulls a chute, and after that point there's enough surface area under that parachute to keep Georgie from falling to the fans and dying, and he starts to go up instead. So the first thing we're going to do is we're going to calculate the position relative to this velocity, and the way we do that is by taking the area under the curve. And I've demonstrated so below right here, and I've done so very nicely with a series of triangles and squares. Each triangle represents about 5 units, which would be meters, and a square represents 10 meters. And we can plot them out at each time point, by just counting the triangles and squares, plus our initial position, which is 2. Can't forget that. And when we do that, we end up getting something that looks like this, which is a parabola. Which makes sense because our acceleration is a constant non-zero value, or not constant at least, but it's a non-zero value, so it's going to be parabolic. So after calculating the position, we can move on to the acceleration, and we could very simply calculate the acceleration by looking at the slope of the velocity versus time charts. We get the slope by taking the rise over the run, the change in the rise over the run. And to do that, from 0 to 4, we take 10, which is the rise, divided by 4, which is the run, and we get 2.5. So the acceleration from time point 0 to time point 4 is equal to 2.5. And it's shown right here. But as we notice, at time equals 4, which is the point at which he pulls his parachute, his velocity changes, because he's now going to start going up. And we can calculate how much it changes, which is the acceleration, by taking the slope again, which is -10, because now he's going down, and it's going from 10 to 0. So the difference is -10 over the change in time, which is constantly going up by 2 for each tick. So that's going to be 4. And you get a -2.5 acceleration. And that remains constant from 4 to 12 seconds. And it's shown below. And this all makes sense because if you think about it, when he pulls his chute, he's no longer being accelerated down towards the ground due to gravity, because the surface area of the parachute is enough to allow the fan to push our poor friend Georgie up and towards the top of the wind tube. And we can see this change in acceleration right here where he's going positive and he's going closer and faster to the ground until he pulls a chute, at which point he starts to go back down and up towards the ceiling. And we can see he gets really close to the ground at like around 40